Just to make sure there was clarity, the reason why I was a couple minutes late is I was adding some information to your Piazza final exam policy post in case it wasn't clear. So if you're a peer tutor and you finished your 10 hours, then you don't have to do anything after homework 10. And you'll have your final web assigned grade after we put the lab grades on there. And if you have a 92.5 or above, so that means you have to have more than 92.49, it has to round up to 93, then you only have to take section 4 of the final, which is a take-home, which we'll be posting by tomorrow. And if you do not, you have to take that plus one other section of the final. And I've put an example calculation for your final grade. Section 4 of the final counts as like 1/10 overall of your exam portion because it's only worth, it's covering 1/10 of your material. So it's covering homework 10. And then what we'll do for the rest of your grade is actually calculate a test 1 material score, a test 2 material score, and a test 3 material score. And those will be the average of your section on the final plus your original test score. But we'll replace one of those with a better score on the final if you have it. So for example, if you actually take let's say you take section 4, which you have to take, and you decide to take sections 2 and section 3, and you get a higher score on section 3 than what you did before, but you get a lower score on section 2, we'll just ignore that. So if you do any extra sections on the final, we will ignore them if they don't help you, and we will replace one grade for you, so if it helps you. Yes? Then you only have to take section 4, and it will count for 1/10 of your score on your tests. So there's 60% of your grade is from tests, so it'll count for 6 points out of your final grade. Yes? It will count. So if you only take one section and it isn't better than your original grade, it's going to be average with your original grade. So you can do worse by taking the final. So pick a section and do better on it than you did originally. Okay? If there are questions on that, I'll be happy to answer them on Piazza. So post any questions you've got there, unless you think you have a clarifying question for now. So mostly the final can't hurt your score. As long as you study a little bit, it won't hurt your score. And homework 10 is the easiest one, so should actually help your score. All right, it's easiest one according to averages, by the way. Not according to difficulty, just according to scores. Okay, so the last thing that we're going to talk about is Hassse diagrams, and we've done a little bit with them before. And we've mentioned that those are actually graphs, directed graphs for partially ordered sets. And we make all arrows go up, so we don't actually have to draw the arrows, we just make them lines, and we remove all reflexive edges, and we remove all transitive edges. Okay, so let's do an example of one. So let's have a set of numbers. Okay, so here's a set of numbers, and we will do divisibility as the relation on them, and let's draw the Hassse diagram for that. So before we do it, let's figure out which numbers divide which. So 1 divides everything, right? All right, and then what does 2 divide? 4, 6, 8, and 12. And 4 divides 8 and 12, right? And 6 divides 12. By the way, I'm not writing that something divides itself, right? Because we're going to remove the reflexive edges anyway. 7 doesn't divide anything else. Okay, 8 doesn't divide anything else. 12 doesn't divide anything else. And 37 doesn't divide anything else. So once I figure that out, I should be able to figure out what the, yes? Did I forget 3? Oh, lonely 3. So 3 divides 6 and 12, right? Thank you for catching that. So you guys are like way in the back, so you should be able to see the most errors. Okay. Finally, you're giving me some feedback now at the end of the semester. You should have started sooner. Okay. We can actually see, what I want to talk about today, more than drawing the Hassse diagrams, which is actually not too hard. Once you can draw a directed graph, it's not that hard to actually arrange it. So it's a Hassse diagram. We will draw it, but first I want to figure out what elements are minimal just based on this, what we just wrote down. So minimal elements in a Hassse diagram are those that are not reached by any other points. So what's minimal here? 1, because nothing else divides 1, right? So let's put a square around that. That's minimal. Are there any other minimal elements? No. If I took 1 out, would there be any minimal elements? So if 1 wasn't in the set, what would be minimal? 2 and 3, and we don't have 5 in the set at all, but if it was, it would be 7 and 37. So we have exactly 1 minimal element, and so if we have exactly 1, it is the minimum. Okay, now how about maximal elements? So maximal elements are ones that you can't go any higher from there. So which ones are maximal? The ones that don't divide anything else, right? So all of these are maximal. Now, since these end in AL, those are adjectives, and that means there can be more than one thing that has that property. Maximum is a noun, and that means there's only one that is the maximum. Is there a maximum in this case? No, because there's not only one. So it is a little tricky that these are actually numbers, and when we think of the word maximum, we normally think of like the biggest one. But since the relation we're considering is divisibility, we're actually asking, is there a maximum with respect to divisibility? So don't get tripped up on the word maximum and just look at the biggest number and say it must be 37, because we're looking at if there is a maximum element in a Hassse diagram is an element that can be reached by all of the other ones. Okay, so there's no maximum here. All right, let's figure out some upper bounds. So upper bounds, so I can look at any element in my set, my original set, and then ask for what the upper bounds for that element are. So let's do an example. So for 2, the upper bounds for 2 include 2, 4, 6, 8, and 12. So everything it divides plus itself is an upper bound for 2. And same thing for 4. So 4 and actually 12 are its upper bounds. So if I wanted to take the upper bounds of the set 2 and 4, then it would be the intersection of these two sets. So the upper bounds for 2 are here, and the upper bounds for 4 are here. So the intersection of that we already know how to do. So the upper bounds for this is the intersection of the upper bounds for 2 and the upper bounds for 4, which is equal to the set containing 4 and 12. So the thing that might be surprising for you there is that 4 is an upper bound for 4. So you might not realize that, but it is. Because remember that even though in a Hassse diagram we don't draw the edge that goes from 4 to 4, 4 does divide 4, right? So an upper bound is anything I can reach from 4, yes. That's a good question. I think someone in the back was going to tell me that too, weren't you? Excellent. Okay, so we actually have to put that in here too. Now, my question next is there a least upper bound? So, least upper bound is easier than it seems. So a lot of times greatest lower bound and least upper bound are trip people up. But what I do is I figure out the upper bounds, and then I see if there's a minimum. If I look at that set and see if there's a minimum in that set that divides all the other things, then actually it is a minimum. So is there a minimum in 4, 8, 12? It's 4, right? Because 4 divides everything in there. And that's the definition of a minimum. So yes. So the least upper bound is 4. So there's only one least upper bound. So minimum, maximum, least upper bound, and greatest lower bound all are asking for one thing. Upper bounds is asking for a set of things, and lower bounds is asking for a set of things. Okay, so let's draw this picture. So we knew that 1 divided everything, and we know it's a minimum, so it's got to go at the bottom. And then 2 is on the next level, and so is 3. And all of the prime numbers are going to be on the next level because they don't have any other dividers. Okay, and then we're going to put 4 on the next level after that. And what level does 6 go on? Same level as 4. And 8, where does it go? One level up from 4. Good. Then 12. Same level as 8. And 37. That's already on there. Okay, so if we put our squares around our minimal elements and circles around maximal, we can really easily do that. Once we've drawn the Hassse diagram, it's really easy to find the minimum and minimal and maximal elements. All right, and then we had asked for the upper bounds of 2 and 4. So the upper bounds for 2 are anything I could reach by going up from 2. So I like to draw a circle around mine. And then the upper bounds of 4 was everything I could reach by going up from 4. And then you take the intersection, which is really easy in this case. That's this little rounded triangle here, or pork chop shape. I don't know what that is. And then when we're looking for least upper bound, it's going to be the minimum in that circled graph. Okay? So within that, 4 is clearly our minimum. So that is the least upper bound for 2 and 4. Any questions so far? Okay, so lower bounds work very much like upper bounds, except we're talking about whether we can go down to reach something from a point. So on this one, let's figure out what lower bounds for 6 are. So we can reach 6 from 6. We can also reach 2 and 3. And we can reach 1. So those are lower bounds for 6. And how about lower bounds for 7? So 6, these are my lower bounds. And for 7, those are my lower bounds. So the greatest lower bound of 6 and 7 is what? It's 1. First of all, it's the only lower bound in the intersection, right? And when I'm looking for greatest lower bound, I'm looking for the maximum in the set of lower bounds. And since there's only one, it is the maximum. Okay, let's do another one where we start the Hassse diagram just from a matrix. All right, so we know that a Hassse diagram is a partially ordered set, so it's going to have ones on the diagonal. In this case, we're going to have A relates to C and D. We're going to have C relates to G. B relates to B. D relates to D, E, and F. E is going to relate to E and also to F. And F relates to F, and G relates to G. And I think that is it, except for C relates to C. So I should have all ones on the diagonal and have some other ones. I'm not going to put the zeros in. Okay, so before, when we were asking whether a set was transitive, does anybody remember what we had to do with a matrix to figure out if the relation was transitive in the first place? Check every possible pair. And how do we do that with our matrix algebra that we learned? Maybe scores will go down on the final. You don't remember how to check for transitive? What about composition? So you guys had to prove that if R is transitive, then R squared is contained in R. That's the definition of transitive. So if I square it, then everything I get in there has to be in the original relation. So let's square this and see if everything we get is in our original relation. Okay, so in order to square a matrix, remember we used our magic wand trick. So we turn the first row into a magic wand, and whenever there's a 1, that's going to be a magnet. It's going to pick up ones when I slide it across. So I'm going to pick up row number 1, row 3, and row 4. So I'm going to pick this one up, and this one up, and I'll OR those 3 together to get my new first row. So from that row, I'm going to get those few, and then I'm also going to get a 1 in the last position, And then from here, I'm also going to get these 3 right before. Okay, so that's the first row. Yes. The second row, we're going to just pick up the second row. Third row, we'll pick up the third row and the last row. So the third row and the last row were together, just gives me the third row back. And this one, I'm going to pick up rows 4, 5, and 6. 4, 5, and 6. If I OR those 3 together, I'm just going to get this one. Okay. So we're looking at the E row. Now we're going to pick up rows 5 and 6. So that's these 2, which will just give me row 5. And then F is just going to pick up the F row, which is all zeros except for on the diagonal. And then G is going to do the same thing. Okay, so this is, so if my relation is R, this is the matrix for R squared. So I was missing some 1s in there, so to make this transitive, I have to put some 1s back in. So these were already in our original set, so I'm just going to compare these with the original. Okay, so the ones in the original are this, this, and this. And all the ones in the diagonal are already in the original set, right? Okay, so C, this one was already in there. On D, all 3 of these were in there. And E, those were already in there. So I just missed a few on the top line. So let's add those back in, because I made this problem up. So anyway, if I square that, I'll still get the same thing back, because this is transitive now. But that's how we check it, is we square it. But then what we can do is, if we're drawing a Hassse diagram for something and it's a matrix, you can square it and then take out all the ones that are in the square, and it actually gives you a whole lot less things to look at for drawing the Hassse diagram. So let's take these out and see what we get. Okay? So actually they're all out. That was a trick that Dr. Bitzer gave me. Well, that's not going to work. I must have made a mistake, so we'll skip that trick I was trying to teach you. Sorry about that. So now, since I can't do the trick because it didn't work, I'll have to see if I can figure it out why it didn't work. Can anybody tell which element relates to the most other elements? It's A. It has the most 1s, right? So it's pretty much got to go on the bottom row. And nothing else relates to A, so it's definitely got to go at the bottom. Okay? Does anything relate to B? It relates to itself, but nothing else does, right? So B also has to go on the bottom. Does C relate? Does anything else relate to C? A does, so it has to go above A. Anything else? No, nothing else does, so I can just put it here and draw that. Okay, so we've done A, B, and C so far. Now D, does anything relate to D? A does, so it can go on this level. But nothing else does, so I can put D here. How about E? What relates to E? A, D, and E. So it has to be above D. So I've done E. And then let's look at F. Does anything else relate to F? Yes, A, D, E, and F. So that's got to go above E. And we're done with that. And then G relates to A and C and G. So where does it go? On the same level with what? E, above the C. So that's how you draw your Hassse diagram. You look at each of the columns. So for each of these, you start to draw a node. It helps if you figure out which ones go on the bottom first. So if you look at the columns, if there's nothing in the column besides a 1 in the diagonal, then you need to put it on the bottom row. So you should have, since it is a partially ordered set, there is always a minimal element. So you always find at least one thing to put on the bottom row, and you always find at least one thing that goes on the top. So, by the way, is B minimal? Is B maximal? So B is minimal and maximal. So is there a minimum in this graph? No, because there's more than one minimal element. And there's also more than one maximal element, so there's no maximum either. So what's the least upper bound of BD? There isn't one because upper bounds of B is just B, right? Upper bounds of D is D, E, and F. There's no intersection, so the upper bounds is empty, and so there is not a least upper bound, so that does not exist. That's what D and E stands for, does not exist. Don't put empty set for least upper bound because we're asking for exactly one thing when we ask for least upper bound. So we're not asking for a set of things. If we ask for upper bounds with an S, we want a set. If we're asking for least or greatest bound, then we're only asking for one thing. Any other questions on this? Okay, so that's all I wanted to do on Hassse diagrams today. So I wanted to allow you some time to ask me some questions or ask me to do some examples from anything that you would like for me to do. We will, by the way, schedule some review sessions after I talk to the TAs about what times they can do. If they can't do any, I will do one. And you have all of your practice tests, so the sections of the final will be very much like the original tests. They will have fewer problems because your exam period is not that short, but that's pretty much the only difference. The question is, should we count on 20 to 25 problems for the exam? There'll probably be like 6 questions on the Section 4 take-home, and you get to do that before you come. So you should count on like 10 problems for each section of the exam like you had on the original tests. So 8 to 10 problems. It's probably going to be closer to 8 for each section, 6 to 8 for each section. So you won't actually have to be here for 3 hours. And by the way, we're also going to allow you to come to whichever section you want. So the exam for Section 1 is actually next Wednesday from 8 to 11. Our exam is December 17th from 1 to 4. I'm going to put up probably a WebAssign thing where you actually indicate which one you're planning to come to. And then as long as there are seats, you'll be allowed to come to whichever one you prefer. Because I understand you might not want to be here on the 17th. I don't want to be here. In fact, if all of y'all come next Wednesday, I'll be so happy. That'll be awesome. Yes? Yes. That's right. If you get a higher score on both of them, so let's just say I do sections 2 and 3, and they're both higher than your original score. Then whichever one is a bigger difference, So let's just say that this one's bigger. Okay, so let's just like way higher. All right? Then what we'll do is T3 is going to be equal to 2 times section 3. So T3 is your score for the test 3 material. So we'll give you that because we're going to replace your original test 3 grade with that. But T2 is going to be S2 plus test 2 grade over 2. So we're going to replace one of your original test grades, and your overall test score for the end of the class is going to have half from your original test grade and half from your new section. There's not a separate score for the final. Like, that's the total thing. So the way that the score works is 3 times T1 plus 3 times T2 plus 3 T3 plus S4 all over 10. And I just put this in the Piazza post. That's why I was a couple minutes late, because I was writing a formula. I actually already have a spreadsheet that calculates it all, and we'll put in all your scores and it will calculate it for us. And so each of this, T1 is actually is the average of test 1 and section 1, if it helps you. So we're only going to do that. So you're only required to take one section. So we will do that for at least one. So your T score for one of those is going to be averaged with whatever you get next week. Yes. Yes. You may only get a worse score on one section. So we'll pick whichever one is the best, and we'll replace your original score if it's better. If it's not, we will average it with your original score. No, you won't be penalized. Like, if you take all 4 sections and you bomb them all, which, believe me, will happen, then what will happen is we will take the least bombed and we will average it with the test score of that. No, you won't be penalized for anything else. No, so if you try some extra sections, that's free stuff. I don't want to grade a bunch of extra sections, so study if you're going to try some more, yes. Next Wednesday from 8 to 11. Wednesday, December 11th. I'm going to put a poll where you actually tell me which one you're going to come to, because there's a limited number of chairs in here. So I'll put the exact date and time and on the poll, and you can pick which one, and then you can put it on your calendar. Yes. Yes, I would recommend that you study the section that you did the worst on and take that one. Yes. Yes. Your cumulative grade thus far is posted on WebAssign, except for homework 10, because it's not graded yet. It's not finished grading, and your lab scores. So those just need to be put into WebAssign, but it's always actually calculating your average based on what's in there. Yeah, they're going to be put in before you vote with which one you're going to do. Yes. Can you still submit homework 10? Yes. But do it soon so your TAs don't kill me. So do it by tomorrow night. Okay? Nobody wants me to do an induction problem? Yes. Sure. Sorry, I have to make it up before I can do it. Okay, so we're going to prove by induction that the summation from 2n to 5n of k is 21n squared plus 7n over 2. I hope it's right. Okay, so for the basis, we need to plug in n equals 1, and that means we have the summation from 2 to 5. So the thing you have to do when you do the basis is just plug in n, and then calculate the left side and calculate the right side and see if they're equal. So this is going to be 2 plus 3 plus 4 plus 5. And the right-hand side is going to be 21 times 1 squared plus 7 times 1 all over 2. Which is 21 plus 7 over 2 equals 14. 9 plus 5 is 14. Yay, I'm so glad they are equal. By the way, what is summation of k equals, what if n equals 2? So what is our statement for n equals 2? What is the bottom? Where do we start? We start at 4. And what is the top? 10. And then how do you unroll this? What is that equal to? No, don't add it up. Just tell me what to write, like I did that. What is it equal to? Summation from k equals 4 to 10 of k. 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. The reason why I wrote that out is it's really easy to make some weird assumptions in your head about what you're adding up and write this thing right here. This mistake happens all the time. Okay, remember that summations go up by 1 every time. Okay, so that k number goes up by 1 every time, even if it looks like there's some weird jumping by 2 formula. We don't get to do like what we do in for loops. It's like k equals k plus 2. We don't do that in summations. It's always k equals k plus 1. All right, so let's do our assumed statement. Yay. Already written out for us. No discrete math humor laughs there. Okay. It's already written out for us. Okay, so now we're going to go from 2n plus 2 to 5n plus 5 of k. We're going to plug in n plus 1 on the other side. And just because it's going to be hard to recognize that when I see it, I'm actually going to multiply that out. You guys like to ride sideways, right? It's more legible like that? I'm just kidding. Anyway, I just want to finish this on this paper. All right, 49 and okay, is that correct? 21n squared plus 49n plus 28 over 2? Okay, good. So I'll write it regular on the other page. Okay, so that's part of our setup. The next thing we have to do with our setup is we actually need to write our proof statement in terms of our assumed statement. some part of it. And I think a lot of you, if you feel like you still don't get induction, you might not have really followed my start with the left-hand side of the proof thing, so I'm going to do it a different way today. So our assumed statement is k equals 2n up to 5n of k equals 21 n squared plus 7n all over 2. Now, I'm always allowed, when I have an equality that I am given to be true, which is what an assume is, it's something that we are given true, I can do the same thing to both sides anytime I want, and it'll still be equal, right? So what can I do to both sides to make it into this summation that I actually want it to be on the left-hand side? So if I want a summation to go higher, it's really easy to do that. I can just say, let me add another summation where k starts at the number after this one, and then it goes up to the number that I would like to have. So that's what I call fixing the top of the summation, right? So now I've just added on some terms that make it so this is actually equal to the summation of k equals 2n up to 5n plus 5 of k, right? Is that completely fixed? No. So the bottom has not been fixed yet. So before I move on, I want to ask if there are any questions about this. Okay, so the next thing I need to do is, this is starting too soon, so what I need to do is take off the terms that come before where I would like to start. So I would like to start at 2n plus 2, and I'm starting too early. So I need to subtract off starting at 2n and going up to 1 less than where I want to be. So I'm going to go up to 2n plus 1. You can also just subtract 2n and subtract 2n plus 1, but sometimes your formula in here might be like k squared or k plus 7 or something, so you might need to do the bounds on the summation so you can make sure you're doing everything right and then plug it in. So what I need to do to fix this assume statement, so this is the assume, what I need to do is add this and subtract that. If we leave the minus sign on there, we're still adding it. Okay, so when I start with my assume statement, I have summation k equals 2n to 5n of k, and I add the fixed top term, and I subtract the fixed bottom term, and I will need to do that on the right-hand side also. So it would be nice if I figure out what these are so I can do that on both sides. So this is equal to 21n squared plus 7n over 2 plus the same stuff. Okay, so this is an equality that I started out with. I started out with my assume statement. I added the same thing to both sides, so now I still have an equals. We have to figure out what these are. This is easy. This is minus 2n minus 2n minus 1. That's what that is. And this one is 5n plus 1 plus 5n plus 2 plus 5n plus 3 plus 5n plus 4 plus 5n plus 5. Also easy, but taking a lot longer to write. And then we just count up what these are. That's 25 plus 3, 6, 10, 15. So what this fixed top is 25n plus 15, and fixed bottom is minus 4n minus 1. So I add those two together to get 21n plus 14. So I'm going to get 21n squared plus, on the right-hand side, I get 21n squared plus 7n over 2 plus 21n plus 14. And so on the left-hand side, we actually can write that this is equal to the summation of k equals 2n plus 2 of 5n plus 5 of k is equal to my left-hand side, and that's equal to my right-hand side, but my right-hand side doesn't quite look like what we want it to, which is this, 21n squared plus 49n plus 28 over 2. So now we need to use a common denominator of 2 to do this. So I should get 21n squared plus 7n plus 42n plus 28 over 2, and hooray, that is what I was looking for, and I'm done. So after you write basis, assume, and prove, you also need to make sure that you figure out how to write the proof statement in terms of the assume statement. And then the rest of it is algebra. So if you're going to leave something blank, leave that last part blank, but please don't skip the part where you actually write the proof statement in terms of the assume statement and fix it. And then replace whatever part of the assume statement you're using so that you actually get as close as possible to the solution. So if you have to skip something, skip the algebra, but don't skip the structure. Any questions on that problem? We'll do an induction with an inequality next. So let's prove an annoying problem. So this is what I want to prove. Prove that log of n factorial is big O and log n. Now, there are two ways to do this problem. There's the I'm not paying much attention, I'm just gonna apply what I know, and there's the I'm going to be clever and save myself some work. Does anybody know how to be clever and save yourself some work? Get rid of the logs. Who likes logs? Nobody likes them. If there's a log on both sides, you can do something to get rid of them. So you can actually raise both sides to the power of 2. So what do I mean by both sides? First of all, the definition of big O, I have to know what that is, right? I need to say that log of n factorial is less than or equal to n log n. That's actually what I need to prove, right? Please don't put any C's in there. I don't want to see any C's on your proofs. I want you to pick whatever constant you would like that makes the problem easy for you and put that in there. Don't put a C. It just makes your life more complicated. So there's a C in the definition of big O, but you get to pick it. So pick a good one. Don't just write the letter C because you're not required to write anything, because if you don't write anything, then C is 1. Okay? So does anybody know what we can do now to make this problem easier? How do you get rid of logs? I want to see if anybody knows besides you. Okay, so I know that most of you are like, turn the page. That's how you get rid of them. Just don't look at them, do something else. Okay? But they are not like, they don't just have to stay there, right? You can take 2 raised to the power of both sides, and that inequality should still hold, right? And 2 to the log of anything gets rid of the log and the 2. So that is n factorial is less than or equal to, oh, that's weird. I don't have just 2 to log something. But what is n log n? It is log of what? Log of n to the n. So on the right-hand side, we have n to the n. So this is the clever, I'm going to skip these stupid logs and make my life easier solution. So if you see logs on both sides of a big O proof, you should get rid of them. And also, the problem I just gave you, I made it up. So if you happen to know the formula for adding up k numbers, you could get the formula for adding up the formula for up to 5n and the formula for up to 2n minus 1, and you get the formula for the one that I just did. And I have to do that crazy stuff. But I don't expect you to remember that. So anyway, then we can do the basis. Where do we start? Don't start at 0. It's not fair for factorials. So let's start at 1. That's nice. Let's just make sure that a few of them work. Well, that looks pretty good. Okay, so there's our basic setup. By now you should be able to do this like with your robot brain, right? And your robot hand. You just write this out. Okay? Now the next thing we need to do is pick one of the sides that looks easier to relate the left or the right-hand sides of the assume and prove. Which one looks easier? The left-hand side or the right-hand side? Okay, how many people would like to start with the left-hand side? How many people would like to start with the right-hand side? Okay, good. So we have majority half-hearted vote for left-hand side. So we start with n plus 1 factorial, and we know that by definition that's n plus 1 times n factorial. Right? So that's an easy way to write the left-hand side of the proof statement in terms of the left-hand side of the assume. So that's just something that we know. This is definition. And so I've always done the problem from left to right, so I'm also going to do it with the assume equals now. So we're going to start with n factorial is less than or equal to n to the n. This is the assume. So just like in our logic proofs, we can start with the given. So the assume is our given. So if I multiply both sides by n plus 1, I still have an inequality that's valid. And now my left-hand side is actually n plus 1 factorial. And I've just done a little proof that n plus 1 factorial is less than or equal to n plus 1 times n to the n. That isn't what I wanted to prove, but it's getting there. So I know this. I've just proved it. It was a super easy proof, and that's what I've been trying to show you to do, is actually to start with something super easy. It is usually super easy to write one of the sides of the proof in terms of one of the same side of the assume. That's what I'm trying to give you, something easy to do. So I know something easy now. But what I actually want is n plus 1 factorial is less than or equal to n plus 1 raised to the n plus 1. So now if, let's call that A, let's call this, actually let's call that B. Let's call that B, and this is C. If B is less than or equal to C, I could be done, right? So that's what we call the magic step. Let's prove that B is less than or equal to C. So we want to prove that n plus 1 times n to the n is less than or equal to n plus 1 raised to the n plus 1 power. Well, I can easily start to simplify that by dividing both sides by n plus 1, right? There we go. So now we have n to the n is less than or equal to n plus 1 raised to the n. Are we done? Yes, that is so obviously true, right? Now we're done. So we've already proved that, so therefore n plus 1 factorial is less than or equal to n plus 1 times n to the n, which is less than or equal to n plus 1 raised to the n plus 1, and we're done. So the magic step is figuring out, okay, after you have figured out how to manipulate the assume statement to get an inequality that is true, you then figure out another inequality. If you put those two together and you use the transitive property of less than or equal to, then you actually get the inequality that you wanted to prove. So that's what the magic step is. So if it wasn't clear before, I hope that did clear it up for you, that we tried to get an easy inequality proof based on the assume, and then we tried to fix it for what we actually wanted to prove. It's an in-between inequality. It's an intermediate one. Now, sometimes if you have a complicated proof, or actually if you have two functions that are really close to each other, this won't work. Because this easy inequality actually will be too big. Only that will happen. But I promise I won't give you a problem like that. But if you try to prove that log of n is less than square root of n, you cannot do it with this magic step because they're too close together. They're actually like very close in size, so it's actually really hard to do this kind of proof. So sometimes when you do this magic step, you actually have to do another induction proof. So you can, any technique that works for doing a proof at this step can be used. So induction can be used there, or truth table, or whatever actually works. Regular math, anything. Does anybody want to request any other kind of problem? Yes. Does anybody have that with them so I can write down the exact problem? There's like one person maybe in here with a trapper keeper that has everything. Does anybody know what a trapper keeper is? They probably don't make them anymore. Okay, one person knows. I had one of those when I was a kid. It was like a notebook with a Velcro closure, so you couldn't lose your stuff. It was the big invention when I was in middle school. Nobody has it? Yeah, I wouldn't have it either. So, oh, you do. The one that's proved by induction, something about exclusive ORs. Yeah, it was on the test. Can you bring it up here? That'd be great. Thank you. Let me resume recording. So this you should do with Robot Brain also. Okay, so that setup should be clear, hopefully. Any questions about the setup? So I just copy down my assume with I prove. And replace all the n's with n plus 1s. Okay, so now when I start to do my setup, I need to figure out which one's easier to modify, the left-hand side of the assume to the left-hand side of the proof, or the right-hand side of the assume to the right-hand side of the proof. Looks to me like the right-hand side is easier because I'm just going to exclusive OR one more term on here. So these are the same thing, but I'm just going to add another thing on the end. So you should be looking for that. So when you're looking for where to start in your proofs, you can start with the left-hand side or the right-hand side, but look for the one that looks easier to do for you. Okay? So we're going to start with the right-hand side of the assume, and we're going to add this last term. So actually, we can start with the whole assume, and we can actually exclusive OR that on both sides. Okay, so the assume had these terms, and the one right up to before that, so S intersect AN was the term right before that. And so we just added this onto both sides of the assume, so we know it's true because the assume is true. We did the same thing to both sides, so we still have an equation that is true. And now the right-hand side looks exactly like what I wanted. So all I have to do is get this to look like this. So up until now, I haven't even had to think about what this whole thing means because I could just copy it and use robot brain. So now I have to think about what it means so I can figure out how to show that these are equal. So there's actually two S intersects here, right? So I should be able to factor it out. Right? That's like having like 2x plus 2y. I can get a 2 out. Right? So they work the same. So exclusive OR is a combination of ORs and ANDs work that way. So I can pull them out. So this is going to be S. Well, actually, I should use this rule, right? So instead of just assuming this thing's going to work, I got to use that. So this is my given rule. So if I have an exclusive OR of two things, I can actually combine them. So I do have an exclusive OR of two things, and each one of them is an intersection of two things, and we have the same thing. So we actually can say, I can say that this is S intersect A1 exclusive OR dot exclusive OR AN exclusive OR with A sub n plus 1. So that's using my given rule on the left-hand side. So I have parentheses around the exclusive ORs from A1 up to AN, and then I have another exclusive OR. So can I take the parentheses out? Yes, because exclusive OR, it doesn't matter the order that you do. Right? So now we're done. So the left-hand side now looks like what we want. I'm glad you asked that question, though, because actually quite a few people miss this. No. That was given. So it was given. The first thing that was given was a distribution rule. So you were given a distribution rule for two things, and we were trying to prove that we can do it for n things. That's right. Yeah, so it's exactly like what you said, is that this now becomes like the A1 up through AN, and this is the AN plus 1 term. So we proved that, like we did that in class for De Morgan's. We did the complement of the union is the intersection of the complements, vice versa. We did that in class. So it's exactly the same proof, actually. Yeah. Yeah, because complements is what makes us flip. XOR doesn't flip anything. So De Morgan's makes us flip operators, right? Exclusive ORs don't. Okay, because exclusive OR, when you do n exclusive ORs, by the way, exclusive OR always is just the number, is whether or not you have an odd number of ones. Okay? So if I'm taking, and so exclusive ORs of sets is like whether or not each element is in an odd number of sets. So it makes sense that I can group up any exclusive ORs because eventually I'm just going to look at the sum of the total number of times each point occurs. And if it's an odd number of times, it will be in the exclusive OR, and if it's an even number of times, it will not. Yes? Let me answer this question. So I think you are asking me this. How do I distribute that? So A exclusive OR B is that So those two things are equivalent right there. And then once you have this, you can knot both sides. So yes. So you have. Mm-hmm. Yeah, right. That's right. Yeah, it doesn't flip the operator because it's the same as if and only if. Okay. Lastly, before you go, I wanted to thank you guys. I didn't take attendance, obviously, so